Today we're going to do section 5.3. First, let's look at the book. Let's see, this page has already been scanned, so I just need to focus perhaps a little bit on the new area. Okay, that should be good enough. And next, page 160 and 161, and that's it. This is today's short section. All right, so let me hold this carefully. That should be good. Move over a little bit. Okay, and then zoom in a bit on top. And then a bit on the bottom. Okay. That should do it. Today we are going to do integration by parts on page 159. Now let's look at, first let's look at page 151. That is the actual definition of the Sturgis integral, okay, which I will show it to you right here. The definition 3 is defined, the Sturgis integral, as you can see, is defined as the limit of the sum of f psi, okay, and then alpha and then the difference of alpha in this summation. This summation is also called sigma delta, okay, just the summation part without the limit. All right, so that's the part we're going to focus on right now. And once in proving integration by parts, once we get the summation done, then the integration is just a matter of taking things to the limit. Okay. So then let me find my page. I lost the page. Here it is. So coming back to page 159, here's the sigma delta. Okay, that is the summation part that we're going to focus on. The first thing we're going to do is rewrite this thing so then it looks like this. So please do this yourself, okay, as I have done here. Let me show you what I did is the sigma delta, which I wrote it out, which is this thing, right? And if you write the whole thing out, will be the first thing plus the second one, etc., all the way to the nth term, right? Now we're going to rearrange the terms such that we have, let's see, which equals to, let's see, we're going to focus on, we'll write out two of them, the alpha 1 x1 f psi 1, and then this one, which, and anyway, so let's see, which is and connected to this one, and similar, and then there's alpha x0, okay, which I wrote it right here. And well, in any case, so once you do the rearranging, okay, and well, do this yourself, of course. Once you do the rearranging, you might notice that eventually then we have we have this. We have the psi 1 alpha x0 and psi n alpha xn, okay? So we write those out. And then, but after that, the rest of it, we can factor out alpha k for each k from 1 to n minus 1. And then with f on the inside of the parentheses, okay? And just this is a matter of thinking about this carefully and collecting the terms carefully. Basically, just come from this equation. So once we have done that, then what we do is we notice that in this case we're going to let psi c. In this case, remember that the psi's and k's are in this order, right? We have x k minus 1, then psi k, and then xk, and then psi k minus k plus 1. So, and then for the endpoints that we might not have, we'll define more endpoints, whereas we'll define psi 0 equal to a and psi n plus 1 equal to b. So then now we have, now that we have done that, then we'll define this thing. This summation, of course, is equal to, once we take it to the limit, is going to be equal to the Sturgis integral. And this thing right here, okay, once we take care of the endpoint, it's going to be this still this integral because it just flipped. And otherwise, it is identical. And then we plus the endpoints that we had before. Okay, now how do we know that to make sure that this is indeed the still this integral? Please consider this part right here, where it equals to, we flip it around, all right? And being that we have taken care of the endpoints, it will eventually, it looks exactly like the still this formula requirement, okay? These are not the, right here, I'm just saying that they are the same form. In other words, we can write this to be this, being that this it satisfies this form. Now, to see that it satisfies this form, please check a few terms, like when k is 0, when k is, well, just k, and k is n, and bearing in mind this situation. So, in other words, I want you to prove to yourself by checking the various points that this is exactly this format. Okay. Now, I didn't say they are the same equation. I said this is in the same format. If it's in the same format, that means this is once taken to limit, satisfy the definition of the still this integral. So please do that yourself. Okay, this whole thing is just a matter of rearranging terms and taking care of some details that to make everything come out. So having said that, then we have basically demonstrated the what is this? The integration by parts theorem, okay, which was back in the day. It means when you integrate u dv, that equals the uv and then vdu or some minus vdu or something like that, right? But we're going to do the same thing now with the still this integral. Next, let's go to next page, page 160, and look at the theorem for integration by parts. And the theorem states if you have one f of x that's going up, non-decreasing, and alpha of x is continuous. Okay, and then if that is the case, then the integration by parts formula works, as is shown here. The way it will works is we just said that this integration by parts formula, okay, the first summation, right, it equals to the second summation right here. And this thing satisfies the still this integral definition. As a result, when we let it go, it especially satisfies because f is, now f is the non-decreasing function, points up, and well, alpha is the continuous function. So by theorem 1, which just says that in those conditions the integral exists and is defined this way, then we prove that the integral on both sides exists, and this equation right here holds. So our theorem is already proved in the previous page. However, there is some point that needs to be mentioned, okay, and we have proven that a monotonic function, that's the f going up, is integrable with respect to a continuous function. All right. Now, however, in this formula, when you look at the formula of the integration by parts, the two are not different. Okay, one is the same as the other in the formula. That is, the formula is symmetrical. What that means is that we can change the condition as f of x is continuous and alpha is increasing. That's fine too, right? And also, of course, as in the previous section, being that we have, when we have learned it bounded variation. So as long as alpha is monotonic, alpha is as long as the function that is monotonic, that is the strictly increasing, we can replace it with functions of bounded variation, then it also works. So that's that. Next, there are a couple of examples. Please do these examples yourself, okay? Because they're very short and straightforward. One of them is redo example B of 1, which is that step function thing. It's a matter of just checking out the details and then applying the integration by parts. Same as this example, example 8. Okay, you do a very simple integration by 2 ways. Okay, and it checks out to be the same. And this one has something to do with absolute value, but that changes nothing. right? And so that's the end of this short section, okay? So for homework, please do, let's see, give me a second here. For homework, which is on page 160, please do problems 1, 3, 5, 7, 8, 9, 10, 11, 12. And use integration by parts when it's reasonable to do so, okay? Or as much as you can reasonably manage. So, and when you're done, I want to talk about the homework. So let's look at problem 1. Problem 1 is a straightforward application of integration by parts, okay? And so I got the answer in here somewhere, and I missed something, and I couldn't get the right answer at first, but once I found my mistake, everything came out just fine. So the answer checks out. That's problem 1. Problem 3 is, I made more mistakes here because problem 3 is a step function, and I drew the step function wrong, so then things kind of fell apart for a bit. But in any case, once I found my way out, then this equal to this thing, okay? What is that? Yeah, apply the integration by parts, right? And then plus the endpoint subtraction and stuff. And once I got out of redid the step function, draw it the right way. This is the actual step function, right? And step functions always mess me up, okay? Because I have a hard time with keeping details straight. But once you get the step function properly, then we get this pack of integration, okay, which end up being 60. Now, how did I get it to be 60? Because I used a calculator, which because I wasn't about to do these integrations myself, and they're not particularly hard to do, but there's too many of them. Okay, I mean, I'll do 1 and maybe 2. Okay, 3 is just, I'm not doing 3 of these things. So anyways, I typed it into the Wolfram Alpha calculator, and remember to type this in. Sometimes it's hard for you to put your cursors in stuff. So if you need to edit the formula, consider using the left-right arrow. Okay, and it helps me because sometimes you want to click here and it wants to be over here or there or something. And the arrows seems to help. And anyway, so I typed it in, and this thing, look how smart this thing is. It's able to add up a bunch of integrations. I mean, that is totally awesome. So anyway, so I was able to crank it out, and it equals to 60. Okay, after I fixed certain mistakes when I typed it in. So, and that is problem 3. Next, let's do problem 5. I think it's a similar situation, except now it's more complicated. We have absolute value and the bracket, okay? So it's another kind of a step function, but if it just draw the step function carefully, I think this might be the graph, whatever. Okay, just draw the required step function, the bracket thing, and then remember the jumps, okay? And then everything comes out pretty good. See, this one, I'm already done here. It's only about 3 lines or so, maybe less. So that checks out with the answer at the back of the book. So that's that. So next, let's look at problem 7. Now, problem 7, we are going to apply integration by parts, but we need to be careful here because integration by parts does have requirements, right? Your function, one of the functions, here's integration by parts on page whatever. Now you notice the function, one needs to be monotone, and the other function has to be continuous. Whereas the bracket absolute value of x is not monotone, okay? Absolute value of x is not monotone, so the bracket isn't either. So then, what we'll do is then break up the integration. Where is it? No, sorry. We're talking about 7. Same situation. We have the bracket absolute value of x, which is not monotone, but we will break it up into 2 functions that are monotone. Okay, so we'll go from -1 to 0 when it's decreasing or non-increasing, and then the other one which is increasing or non-decreasing. Now, and the next thing we have to pay attention is the function. The other function, this one, has to be continuous, and of course we're going over 0 where we have 1 divided by 0 here. But this function does, when as x approaches 0, it approaches 1. Okay, and so as a result, we redefine this function as equal to this thing normally, and then as 0, we'll define it as 1. And if we do that, the function will be continuous. Okay, that is because, well, whatever, you can go through this in your head real fast. That the function, it does go, because the function goes to 1, okay, as x approaches 0. So we'll just call it 1. And anyway, so now that we've done that, and so we break up this thing into 2 chunks. Then each individual one is defined, right, by theorem 1 or whatever. So then together they will define the combined integral as the sum of the individual ones. Now once we've done that, then we calculate to calculate this thing, then we calculate each one of these things. So that's what I did here. This is from -1 to 0, which I end up having 0. And this one from 0 to 1, which is also 0. So the total is 0, and which checks out at the end with the answer at the end of the book. The answer really is 0. So next we'll do problem 8, which is exactly as the same as problem 7, except that now we're integrating from -2 to 2 instead. Okay, so that's what I did. Okay, continuing, let's stare at this thing. If we do that and we do the same trick, apply the same formulas, right? We'll do from 0 to 2 and then end from -2 to 0. And don't forget the negative sign here in the integration by parts formula, adding bits at the end, you know, the alpha B FB and alpha A FA or something. Let's see, what does it say? Yeah, alpha B FB minus alpha A FA, which I have taken care of here. So all said and told, it equals to a bunch of stuff that eventually equals to this, okay? When I ran out of space here, so I wrote the final answer here. And because some of it got subtracted out, like right here we have plus F2 and then plus F, and I think it's minus, yeah, minus F2 and plus F2 times 2. So anyway, when all the dust settled, that this is the answer, and these and this one together, okay? And it does check out. That's the same as the answer as the back of the book. And so that is problem 8. So next, let's look at problem 9. Problem 9 is we have bracket x, okay, and so on. That sounds pretty complicated, but bracket x is, we're only integrating from quarter to 3/4. And in that range, bracket x equal to 0, okay? And then, so in other words, it's a constant function. If it's 0, then it doesn't matter what this does, right? The whole thing is just 0. And so, or put it another way, so I did that. I actually used the integration by parts. Applying the integration by parts formula we got here, which is so then. And this is the function bracket 2x, but that changes nothing. The bracket x is still 0. Okay, and the rest is 0, so everything is because the bracket x is a constant function, so the whole thing's still gonna be 0. It's that simple. Yeah, so there's nothing going on in problem 9 basically. And so next, let's look at problem 10. Now problem 10 is very similar to problem 9, right? I mean, look at this. This is the same as this part, except for the integration limits has increased to be somewhat bigger. Now what happens then? Now if you draw out these two bracket functions, you notice that they both have a jump at 1, x equal to 1. And that's going to pose a problem because one of the functions has to be continuous. If it isn't, then it cannot converge. I mean, what's f of psi of k supposed to be? You know, is either one or the other, and it will bounce around infinitely and never settle down. So then you can't do the summation. Okay, you can't forcing it to be 0 is not settling somewhere. It's constantly bouncing between two possible values, and as a result, this is why this integral cannot exist, which checks out with the answer at the back of the book too. And so next, let's look at problem 11, which states that, let's say if f is in C1, so it's differentiable, and then alpha x is in C, and then then the integral exists. All right. And okay, now notice that in this case, we didn't say that alpha x is monotone increasing or decreasing, okay? And it could be wobbling, it might not even be any such thing. So, however, we can, but it is in continuous on a closed interval, so it's not going to go to infinity or anything like that. So, and knowing that, let's look at this problem. We are gonna first. I have written down the first line is just the definition of the Stilger's integral. And then I copied down the equation 3 on page 159, which is the formula used to prove integration by parts, right? And so let's look at this part, the summation part. Let's look at it more carefully. We'll put the constants at the end as k, okay? And then what we're going to do is look at this thing. Now it becomes f psi k minus f psi k plus 1, which will apply the mean value theorem on page 9. So this difference is the same as f prime of eta of k, okay, with psi k minus k plus 1 minus psi k, which this is just the identity function, and it is increasing, okay? Yeah, so then as a result, we can apply Duhamel's theorem that, in about 20 pages later. By now, it's 13 pages later. So let's look at it. The Duhamel's theorem on page 173 states that, first let's find it. Okay, here it is, right? We have the condition of, let's see, the Duhamel's theorem, right now our alpha x is just x, all right? So it is increasing. And so then, let's see. So then when you have this situation, even though you have psi f of psi k and g of eta k, and we can, it will still converge to this particular integral, okay? So we're gonna apply that on here, and let's see. And being that, yeah, we said that f is differentiable, okay? And so it satisfies the requirement. So this whole thing, f is differentiable. What else is f? Let's go back to our page here. F is continuously differentiable, and alpha is continuous. That's the given. So which means that in this summation, these two things, where is it? Okay, right here. These two things, alpha and f prime, are both continuous, okay? So f prime doesn't just exist, it's also continuous. So they're both continuous, which is, and then whereas this function is monotone, is an increasing or non-decreasing function. So then the Duhamel's apply. Theorem applies. Let's look at it again to make sure. Okay, it doesn't hurt to look at the theorems that you're using to prove several times, right? See, Duhamel's theorem requires f and the two functions inside here has to be continuous, right? And then this function, the difference function, has to be non-decreasing. So that's that, which we have it both satisfied. So then, so this is let's see, where is it? Find it. Can't find it. Where's Duhamel's? What problem? Oh, right here. Okay, problem 11. So then by Duhamel's, then this condition is, both functions continuous, right? That's the non-decreasing. Therefore, we can apply Duhamel's, and where the limit of this thing is equal to this, which means it exists, and that's all we have to do is prove existence. Okay, so finally, let's do problem 12. Problem 12 states that if we have a function that's in C with alpha of x is alpha is defined as the integral of something else. Okay, anytime you see this thing right here, this kind of an integral, then you automatically think about the fundamental theorem of calculus. Okay, and then and so we have to prove this situation happens. Okay, and that's because by the fundamental theorem, d alpha prime, that is d alpha by dx, is equal to g of x, right? That is what the fundamental theorem says. So then the whole thing comes out quite nicely. Let's see. Okay, So I have written out here. Where is it? If alpha of x is that integral, then alpha prime of x equal to g of x by the fundamental theorem. And then and also being that g of x is given as continuous, then alpha prime is continuous as well, which means alpha is in C1. All right. So then we'll use the theorem 2 on page 156, which states that if you have d alpha and alpha is in C1, then it's the same as alpha prime dx. Okay, and being the alpha prime is g of x, then the equation holds. So let's look at equation 2 on page 156 again to be sure. Okay, let's see. Equation 2 on page 156 says f is continuous and alpha has to be in C1, okay, is continuously differentiable. So if that applies, then f d alpha is f alpha prime dx, right? And that which is the same situation as the Riemann integral. So that is what we have here. See, f is continuous. That's given. Alpha prime is in C. Alpha is in C1 because of this story, and therefore this all works out very nicely. See, so then that equals to alpha prime dx, and alpha prime is g of x, and that's how we proved got to the end of the problem, and that should be the end of this section.